Everything we keep doing keeps building up to more and more important things. This is 2.4. It's back to rates of change and tangent lines. We've got our Wile E. Coyote example. He's chasing the road runner. He falls off the cliff. He has got this position function of S of t equals negative 16t squared plus 900. Instead of looking at this numerically but plugging in a bunch of values, we're going to look at this graphically. And I've got it graphed here. We basically can see that at 0 seconds, if this is time in seconds, Wile E. Coyote is here, which if we count up 1, 2, 3, 4, 5, 6, 7, 8, 9 is 900 feet. Okay? If we want to know Wile E. Coyote or his position at 0 and 5 seconds, his position at 0 is 900. His position at 5 seconds, we would simply go over to 5 seconds and count up to where we see the graph, and that happens to be 500. So his position at 5 seconds is 500 feet. So he's fallen 400 feet in those 5 seconds. So let's draw the line that passes through these 2 points. We have a line that goes through here and here. This line is called a secant line. A secant line is any line between 2 points on a graph. Now, because we have 2 points on a graph, I can find the slope. The slope of that line would be the change in its position over the change in time, which in this case would be 900 minus 500 over, and because I started with 900, I'm going to start with 0 minus 5. That would be negative 400 over 5. I'm sorry, it'd be 400 over negative 5, which is still negative 80. Now, question is, what does it mean? Negative 80 what? Well, change in position is in feet. We have gone down 400 feet. The change in time is in seconds. So this is simply 80 feet per second, which means that it is the velocity of Wile E. Coyote in those 5 seconds. It's actually the average velocity of Wile E. Coyote between 0 and 5 seconds. Okay, so what we have here is we have a secant line that is any line between 2 points, and its slope is the average rate of change of the original function between those 2 points. Now, to get an idea of how this is going to work, we're actually wanting to find out how fast Wile E. Coyote is moving at exactly 5 seconds. And if you remember 2.1, we did this, I think, at 3 seconds. But we kept getting closer and closer and closer. We found the difference in the slopes. Just to have something a little different, we're going to look at this function here. What I've done here is graphed negative 16x squared plus 900 on my Inspire calculator here. We're going to have the calculator generate the slope for us, and I can pick my points. I'm going to leave the 500 there, and my slope between 0, 900 and 500 is calculated at negative 80 already. So what we're going to do here is I can move this point by hand, let's do this on the computer. I can move the point by hand, and I can get closer and closer to 5, and the secant line still has 2 points, and my slope keeps changing. Notice that the slope keeps getting bigger in the negative direction, and the closer and closer I get to this 0.5, the closer and closer I seem to get to about negative 160. Okay, now, to answer the questions on your paper, I can simply type in some numbers here. So I'm going to do this from way over here. So we're going to go from 4 to 5 seconds. We have a slope of negative 144. From 4.5 to 5 seconds, we have a slope of negative 152, or negative 152 feet per second. I can get closer than that and go 4.9. And I'm at negative 158, and I can keep going here. I could even get closer, 4.999, or 4.99, and I'm at negative 160. And if I were to zoom in here, let's go zoom box. Just a little box right there. I can still see the 2 points are not right on top of each other. My slope is negative 160, and as I get closer and closer, I can drag this thing. I can keep zooming in here. And I can drag these points closer and closer together. Question is, what do you think is the graphical interpretation of the line as I get closer and closer and closer to this point? Well, if you said the tangent line, you would be correct. Two things to understand here. A secant line is a slope, is a line between 2 points that we're going to calculate the slope for. A tangent line only has 1 point, and we're going to need limits to calculate the slopes of these things. So, how does this work? Well, we can approximate the slope of a tangent line using a secant line. You got this picture on your paper. I'm going to bring this up one more time just so you can see how this works. Again, I'm going to grab this point and I'm simply going to move it closer and closer. Now if you notice, this point is h spaces to the right of P. Q is h spaces to the right of P. So I've got my point P is A, f of A. My point Q is h spaces to the right. So this would be A. This would be A plus h. And if I plug it in, I get f of A plus h, which means the height of this rectangle or triangle drawn here, which would be the change in y, is simply f of A plus h minus f of A. And the change in x, this distance, is simply h. But what I'm going to do is I'm going to get this secant line slope, and I'm going to keep going closer and closer and closer to this point, and I'm going to make that distance between the 2 points almost nothing, which means I'm trying to make h go to 0, which screams to me, use limits. Okay? So how does this work? Well, we can say then that the slope of a curve at any point, a f of A, is the number m, which is slope. We've been using since Algebra 1. It is the limit as h goes to 0. There's h. H is going to 0 of f of A plus h. That was our change in y, and this is our change in x. And we want h to go to 0. Notice if you plug in h equals 0, you end up with f of A minus f of A over 0, which is 0 over 0, which means you're going to have to do something else that we did in 2.1. So everything you learned in 2.1 is going to come back for every single one of these problems. You're going to have to simplify these limits algebraically. But this is the coolest part. We can find the slope of a line that only attaches at this curve at one place, not two. But we're going to use it by finding the limit of the secant line's slope. This is the slope of a secant line. And we're going to use a limit of the slope of a secant line. Now this thing has a name. It's called a difference quotient. Again, incredible vocabulary skills. It's called a difference quotient because you are subtracting and dividing. Your goal is to simplify this difference quotient. What that means specifically is to cancel the h in the denominator by doing some kind of correct algebraic manipulation. There's a lot of ways to cancel h that aren't correct. You got to learn to do it the right way, and the only way you can cancel h is if you can get an h all by itself in the numerator that has been factored away from everything, and it'll cancel. Okay? To get an equation of a tangent line, which is what our goal is, we now know how to find slope. We can find the slope using the limit as h goes to 0 of the difference quotient. We will also have a point P. So if I have a point and a slope, it's a piece of cake. However, there are some functions that have vertical tangent lines. And if you remember from algebra, the vertical line has no slope. So there will be no limit as h goes to 0. The limit will not exist. So we're going to use this definition that's on the screen here, where we have if f is continuous. That's important because if it's not continuous, then it may not have a limit either. It may have a vertical asymptote. But if it's continuous at our point and the limit turns out to be non-existent because the limit goes to infinity or negative infinity, then we're going to say that there's a vertical tangent line. Now, keep in mind, the limit doesn't exist, the slope doesn't exist, but there is still a tangent line. All right, what kind of graphs have this kind of weird stuff going on? Well, if you were to look at something like y equals the cubed root of x, just as one example, the cubed root of x comes down here and gets flattened out and goes up this way. Right in here at 0, there is a vertical tangent line. If you were to ride this roller coaster, right there at 0, you'd be going straight. You'd be going kind of flat, and then you'd be going straight up and down as you go out and past 0. But at 0, you'd be going straight up and down. There's not that there's anything wrong here. It's just the tangent line is vertical, so your limit definition is going to turn out to be non-existent. Those cases will come up every once in a while. But what's more important so far is that you understand right now that the slope of a curve, not a slope of a line, the slope of a curve can be found by using the equation of a slope of a line between 2 points and forcing those 2 points to get closer and closer to 0. All right, let's try this. Before we get used to this definition, we need to make sure we're comfortable with f of a and f of a plus h. I find that a lot of people, we don't do this, start off on the wrong foot. So if f of x is 1 over x, what is f of a? Well, f of a would simply be 1 over a. Instead of x, you plugged in an a. It's not that hard. Well, for some reason, once we start plugging in more than one thing at a time, it gets confusing. All we did was take 1 and divide it by what we plugged in. So what is f of a plus h? Well, if f of x was 1 over x, then f of a plus h is 1 over a plus h. That's all there is to it. In this case, f of x is equal to x squared minus 4x. So if we're going to plug in a, we get a squared minus 4a. And if you notice how I'm doing this, some of you may want to take the same approach. F of x equals x squared minus 4x. We put it in a parentheses, and then what are we going to plug in? We're going to plug in a plus h, which means we square a plus h. And be careful, you got to FOIL that out, or just know how to do it. I would suggest learning the shortcut. And then we're going to plug in a plus h. All right, how does it work if we got the square root of 4x plus 1? Well, f of x equals the square root of 4 times x plus 1. And if I'm going to plug in a, I get the square root of 4 times a plus 1, which you don't even need the parentheses in this problem. It would simply look like that. If you're going to plug in a plus h, again, you have f of x equals the square root of 4x plus 1. And if you're plugging in a plus h, you're going to get 4a plus h plus 1. Make sure that you distribute the 4 this time. And if you were to simplify this just to make it look like the one above it, it would actually end up being 4a plus 4h plus 1, all inside the square root. All right, now that you got that down, how does this work? Well, back to example 1. Our function was f of x equals negative 16x squared plus 900. That was our position function. I changed it from s to f, just for fun. So find the slope of the curve. You see that right there? You need to make sure you understand what that definition, the slope of the curve, is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. And in this case, a equals 5. Now, you could go ahead and plug in a equals 5 right away and do f of 5 plus h minus f of 5. I would be okay with that. I would be willing to do some of those in the class. I'm going to leave it as an a, because that way we can evaluate it at any value of a. And as we go through and we start chapter 3, we're going to use an x instead of an a every time. So we'll go ahead and get used to using the letters instead of a number. All right, so how does this work? We take the limit as h approaches 0. Please write that every single time until you plug in h equals 0. F of a plus h is f of x here. So it's going to be negative 16 times a squared plus, or x squared plus 900. In this case, we are plugging in a plus h. Now, that is all the first part, f of a plus h. We are subtracting f of a. Well, what is f of a? It is negative 16 times x squared plus 900. And we are only plugging in a in this case. All of this is divided by h. Now, if you're getting the idea that this is going to take a little bit of room, you're starting to get the hang of why I spent so much time making sure you understand how to plug in f of a and f of a plus h. We now need to simplify this. Our goal, number one goal, simplify the difference quotient, then evaluate the limit. Our difference quotient is not simplified till I can cancel that h. Otherwise, I will always get 0 over 0. Okay, so the way we're going to do this is simply some algebra. We're going to beat it to death. I've got to square a plus h, which means I've got negative 16 times. Now I would suggest you learn how to make sure you square this quickly so you save yourself some time. A plus h quantity squared, if you FOIL it out, is the first term squared plus the last term squared plus double their product in the middle. That's 2a plus h's. Then we've got plus 900. Then I'm going to distribute this negative sign so it becomes plus 16a squared minus 900 all divided by h. All right, now I've got to take the limit as h approaches 0, and I'm going to distribute my 16. That's negative 16a squared minus 32ah minus 16h squared. The 900s are gone. Plus 16a squared all over h. Some of you have already noticed the negative 16a squareds are gone. So I can keep going. I know what you're thinking. Oh, it's awful. But you know what? This is how it works. Negative 32ah minus 16h squared all over h. That's all that's left. But I want you to notice in both of these, I have an h. Now, you can do this in a little bit simpler terms, but I'm going to go ahead and do this one small step at a time. I am going to factor out the h from the numerator. That h squared turns into negative 16h all over h. Now I can cancel these h's. And not until then. Make sure you do it correctly, because now you are evaluating the limit as h approaches 0 of negative 32a minus 16h, because these both became 1s. Now notice, it is h that's going to 0, not a. A is just going to stay in my problem. So I'm going to have the limit as h approaches 0 is going to equal negative 32a minus 16 times 0, which means my limit equals negative 32a. Now what in the world was that limit equal to? That limit was equal to my slope. That was the slope. So this is the slope of my function. The slope of f of x, which was equal to negative 16x squared plus 900 at any value of x equals a. Okay? Makes sense that this should change. The slope is dependent on what a is. It's not a line. The slope is changing. The slope depends on whatever x value you pick. In our case, we wanted the slope when x, or in this case, a equals 5 seconds. The slope when a equals 5 is simply negative 32 times 5, which was negative 160, in this case, feet per second. Next example's got normal lines. Normal lines are lines that are perpendicular to the tangent line. So if you've got a curve and you've got a point, you've got this tangent line going through, and the perpendicular line would be there. Those slopes are opposites and reciprocals of each other. Okay, so let's find the slope of the curve at x equals a. Well, that involves taking the slope, which is going to be a limit as h approaches 0 of f of a plus h minus f of a all over h. Memorize it. You're going to need to know it. All right, now that I got my marker picked back up, limit as h approaches 0. What is f of a plus h? It's 1 over a plus h. That could be in parentheses, but it's not necessary. Plus 1 minus 1 over x, which is now a plus 1, all divided by h. Okay, now, do you remember 2.1? You had fractions, you were subtracting, you were dividing, you had to find a limit. So we're just going to simplify the fractions so that we can cancel everything out. I think it's easier if we write this as 1 over a plus h plus 1 minus 1 over a plus 1 times 1 over h. Now, in order to subtract these two fractions, I need a common denominator. I have a plus h plus 1. I'm going to multiply the bottom and the top by a plus 1. Over here, I'm going to multiply the bottom and the top by a plus h plus 1. And then I'm going to simplify my fractions here. All right, so I've got limit. Notice it shows up every single time. It does not disappear until I evaluate it at h equals 0. Okay, this fraction, they have a common denominator of a plus h plus 1 times a plus 1. We're not going to FOIL that out, and we're just going to leave it. This part becomes 1 times a plus 1, or a plus 1. Notice there's a minus 1 again, so that's minus a minus h minus 1 times 1 over h. Okay, if you notice, a minus a goes away. 1 minus 1 goes away. So all you're left with in the numerator here is a minus h over a plus h plus 1 times a plus 1. Well, this is a good thing because I'm multiplying it by 1 over h. This h cancels with that, becomes 1. This is a negative 1 because of the negative sign. And now I can evaluate my limit as h goes to 0, making sure the only thing I now have an h here is right there in the middle of that fraction. So this is going to be negative 1 over a plus 1 times a plus 1, or you could write it as negative 1 over a plus 1 quantity squared. That becomes your formula for the slope of f of x at any x equals a. Okay, the slope is dependent on a. So what if I want to find the slope when x is 2? Well, all I have to do is plug 2 in where there's an a. So we're going to have the slope equals negative 1 over 2 plus 1 squared. That's 3 squared is 9, so it's negative 1/9. Okay, right. How do I find an equation of a tangent line? Well, to write an equation of a line, I need two things. I need a point and a slope. Well, when x is 2, I just figured out the slope was negative 1/9. When x is 2, that gives me the x value of my point, and I need to plug my 2 into my original function. My original function, if you don't remember, was 1 over x plus 1. So this is 1 over 2 plus 1, also known as 1/3. So my point is 1/3. Okay? So my equation of my line is in point slope form, negative 1/9 times x minus 2. I told you at the beginning of this chapter 1 that we would spend half a page finding the slope. I don't know if you believe me or not, but I hope you do now. That is the equation of your tangent line. Now, what's the equation of a normal line? Well, if it's at the same point, I can use the point from here. So it's y minus 1/3 equals the slope times x minus 2. And the slope, which was negative 1/9, the normal slope will just be positive 9 over 1. And there's the equation of the normal line. So how hard is this to do? Only as hard as it is to simplify that limit. And the more you do this, the better you're going to get at it, because you're going to realize that those 3 examples from 2.1, finding those limits, are really what you're going to have to work on the most in this course. Okay? So, we find the limits. That gives us a slope. We use the slope and a point to write the equation of a tangent line, and the normal line, we just flip the slope over. Piece of cake. Nothing hard about that at all. I think that concludes 2.4. It also finishes up all of Chapter 2. So we got a couple days. We'll have a test in Chapter 2. Make sure you got all those note cards made up. Start on the review. Get on that homework. And we'll see you in class.